Okay, so let's talk about end behavior and horizontal asymptotes. First, let's do a little review, right, about limits. So remember, a limit represents the behavior of a function near a particular point. So we're talking about the behavior of a function, which is really just the y value. So think of limits as the behavior of the y value around an x value. So what is y doing as x does whatever it does? Okay. Okay, so we did problems like this. Limit of 2x as x approaches 1. So treat this as y equals 2x. I want to know what the y value is as x approaches 1. Well, we did this with tables. So we picked points very close to 1 on the right side and the left side. And then we evaluated all the y's for those. And then we did our pattern recognition. So it looks like this approaches 2 from the left and 2 from the right. So we said the limit was 2. Right? But remember, in most cases, we want to find a limit is finding the y value around an x value. Well, if we're trying to find a y value, then why not just plug it in? So we could have done the limit of 2x as x approaches 1, just evaluated the y value of 2x at x equals 1. So 2 times 1 is 2. Okay, so keep that in mind. Limits are pretty much the behavior of the y value at or around an x value. Okay, so if we want to find the y value, plug in the x value. All right, so let's try this. Let's evaluate each one of these limits. So we have limit of x squared minus 2x plus 1 as x approaches 3. So let's use our evaluation. We want to treat this as y equals x squared minus 2x plus 1. We want to find out what y is at x equals 3. So substitution. So we'll just plug in 3. So I'll get 3 squared minus 2 times 3 plus 1. And that whole thing should equal 4. So the limit of this whole thing is 4, which means the y value approaches 4 as x approaches 3. So when we get to 3, the y value will be 4. All right, let's try this. So now let's do the limit as x approaches infinity. So I want the limit of 2x minus 1, but now not as I go to a point, but as I go to infinity. Well, same thing applies. Here I have y equals 2x minus 1. I want to figure out what happens as when x equals infinity. So let's do substitution. So I can do 2 times infinity minus 1. And so when you're working with infinities, right, this isn't the 8th grade game or the little kid game of, infinity squared, 4 times infinity. Infinity is infinity. So 2 times infinity is infinity, right? Infinity minus 1 is infinity. So it doesn't matter that there's a 2 and a minus 1. This is infinity. Okay? All right, so we can evaluate infinite limits. Limits at infinity the same way you evaluate, regular limits at a point. Just plug in the x value. All right, so we want to stop this and complete class or problem number 1. Okay, so let's talk about end behavior. So end behavior is simply the behavior of a function as x goes to positive infinity and negative infinity. Okay, which means that the function is going to go all the way to the right and all the way to the left. So now you can kind of see we're talking about as x goes to plus and minus infinity, this is set up for limits, right? So, but an end behavior is what's happening at the end of the function. And the end of the function is where x is infinity and y, and x is negative infinity, positive and negative, right? So let's take this. We have a nice function. This is just linear, y equals x. You can see that as x goes to the right, as x goes down to infinity, y is going to go to positive infinity, right? So as x goes to the right, y goes up, and this will happen forever. Right? And as x goes to the left, y goes down, and this will happen forever. So when I get to the end of the x's on the right, I'll get to the end of the y's in the up direction. And when I get to the end of the x's on the left, I'll get to the end of the y's in the down direction, which means, so let's try another one here. Let's say I have something like this. Now I have a square. So as I go to the left, the y's go up, and as I go to the right, the y's go up. So it doesn't matter which direction I go. As x goes to plus or minus infinity, the y's will end in the positive infinity direction. Let's try one more. So if I do something like this, you can see as I go to the left, my y's actually level out. They don't go to infinity. It looks like they level out to about y equals 1. And as I go to the right, my y's look like they level out to about the same, y equals 1. Okay, so end behavior can either be infinite or it can level out to an x value. It can level out to a y value. That's actually a horizontal line. All right, so when you look at end behavior, just ask yourself, what are the y's doing as the x's go all the way to infinity and all the way to negative infinity. That's all we're doing. Okay? All right, so how do we state it? So this is our first one. This is our f of x equals x. We showed that as I go to the right, y goes up. As I go to the left, y goes down. So here's how we state it. So one way to state it is with this directional idea. So you can say as x goes to negative infinity, which means left, y goes to negative infinity, which means down. Right? And the other way would be as x goes to infinity, y goes to infinity. Okay, so we can use it with these directional kind of notations. So it's not a bad way to do it. In fact, in lower levels, they explain it this way. We're a little more sophisticated, though, so we can use limits. So we can actually do the as x goes to negative infinity, we can use that as our limit base and do limit of the function. And remember, the answer to the limit is what y is doing. So this is saying the limit of f of x as x goes to negative infinity means that y will approach negative infinity as well. So you can see in this one compact notation, we get all of this. As x goes to negative infinity, bam, right there. Y goes to negative infinity, bam, right there. Okay, so we can be more sophisticated and use limit notation. All right, so now the other one, as x goes to positive infinity, y goes to positive infinity, which means the limit, right, of this function as x goes to positive infinity would be infinity. Okay? Okay, so let's see, take these two limits. Well, is this true? Do we have to have the graph to see this? No. We could have evaluated the limit. We have the function equals x here, so f of x equals x. We could have just done our substitution. So set up the limit as x approaches negative infinity of x, do your direct substitution into x, you'll get negative infinity, which is negative infinity. You get the same thing. So algebraically, I could have figured this exact thing out. And same thing for the positive. As x goes to positive infinity, I'll just substitute it in for x. It looks like x is infinity, and then that's infinity. All right, so I could have done that substitution and that evaluation to figure out the exact same end behavior, which is a nice little key concept here. The limits as x goes to positive and negative infinity are the end behaviors. Okay? All right, let's try our last, or one more. Or actually, we're going to do two more. So here we have our x squared. And so as I go to the left, I go up. So as I go to negative infinity, y goes to infinity. As I go to the right, y goes up. So as I go to x goes to infinity, y also goes to infinity. I can do this in our limit notation. So the limit of g of x as x goes to negative infinity. So it's the limit of g of x as x goes to the left is infinity, right? All matches. And then same thing for the right side. The limit of g of x as x goes to infinity is infinity. So this is just saying as x goes to the right, the y values of this go to infinity. All right. Okay, let's do our same thing for the limit. We knew we could figure these out algebraically as well because we have g of x as x squared. So we can do the limit as x approaches negative infinity of x squared. So let's do our direct substitution. So I'll put negative infinity in for this x squared. And a negative infinity squared is a negative, which is positive, and infinity squared is infinity. So it's a positive infinity. Okay, and then same thing for the positive side. Now I'm just plugging in a positive infinity, and infinity squared is infinity. All right. Okay, let's do our last one. So we had this weird looking graph where they didn't go to infinity. So you can see as I go to the left, it looks like y goes to 1. So I'd write as x approaches negative infinity, y approaches 1. And then as x approaches infinity, y approaches 1. Write this in limits. Then it'll be limit of h of x as x approaches negative 1 equals 1. So remember, this tells me where I'm going with my x's, and this tells me what the y behavior is. Right? Same thing here, except I'll just use a positive infinity. All right. So when I represent end behaviors or state end behaviors, I can use this directional notation, or I can use limits. All right, so let's stop this, and you want to complete classwork problem number 2. All right, let's do a little notes here. So we're going to talk about horizontal asymptotes. So a horizontal asymptote is simply a horizontal line that the function approaches as x approaches positive and or negative infinity. I just use the and and the or because there could be two different asymptotes, horizontal asymptotes. All right, so some notes here. The first thing is you can cross horizontal asymptotes all day long, right? You can't cross a vertical because a vertical is undefined, right? A horizontal line here, there isn't any undefined points. There aren't any. So when I get to infinity, right, it's just going to level out to whatever it levels out to. All right, the next is there can be either no asymptotes, one asymptote, or two horizontal asymptotes. Right, those are your only choices. Okay, and the last one is a horizontal asymptote is stated as y equals c. It's a horizontal line. So when I ask you to state the horizontal asymptote, you write it as a horizontal line. Y equals some constant, some value. All right, it will not equal infinity because that's not a horizontal line. Okay, so let's try this. Let's state the horizontal asymptotes for the given graph. Well, we know from before that as I go to the left, approaches 1. So as x goes to negative infinity, y goes to 1, or I can state that as a limit of h of x as x goes to negative infinity is 1. As I go to the right, y also approaches 1. So y equals 1 is the horizontal line that both of them will approach. So the horizontal asymptote is y equals 1. All right, so notice I did the y equals 1. It's a horizontal line. Okay, so stop this and complete classwork problem number 3. Okay, so now let's talk about horizontal asymptotes and rational functions. So it's a really nice thing since horizontal asymptotes occur at plus and minus infinity, so it's the infinite part, we can actually evaluate rational functions with ease. So if I have something weird like this, so rational just means, a fraction of functions. I have a polynomial on the top and a polynomial on the bottom. So if this is the case, then since the x will go to infinity, as I get larger and larger, this x squared will overpower all these other terms, right? So 100 squared is much bigger than 100. A million squared is much bigger than a million. So as the x gets larger, this will take over. And same thing, this x cubed, well, 3 times x cubed, but the 3 is not going to do anything, right? But this x cubed will dominate all of these terms. So since we're going to infinity, we look for the dominant terms, and the dominant terms are just the highest powers. So I can actually treat this as simply an x squared and a 3x cubed. So it'll be an f of x equals x squared over 3x cubed. So, and I can only do this when I'm looking at the function at infinity, because it's the big numbers. Once I plug in bigger and bigger numbers, it's the large powers will take over. All right, so make a note of that. You can only do this cool simplification, this dominating idea, when x goes to infinity, plus or minus. Okay, so let's find the horizontal asymptote by evaluating the limit of this function as x goes to positive and negative infinity, right? So remember, horizontal asymptote is what happens at plus and minus infinity, so evaluating the limit at plus and minus infinity is the actual horizontal asymptote. So let's start with positive infinity. I'll do the limit of this whole thing as x approaches infinity. And now notice I have an x cubed in the top, that's the largest power, and an x squared in the denominator, that's the largest power in the denominator. So I can get rid of all of these terms because this will dominate as I go to infinity. So this limit's actually the exact same thing as this limit. All right, I can just erase the non-dominant terms because they're going to fall off as x gets bigger and bigger and bigger. Well, now I can simplify. I have x cubed divided by x squared. So a cube divided by a squared is a 1. So this will just be an x. And now how do we evaluate limits? We just plug in the x value. So as x goes to infinity, limit of x is just infinity. Okay. All right, do the same thing for negative infinity. You can see I'm going to have the exact same function, so I don't need to go through all this again. I know it's just going to equal this. The only difference is there'll be a minus infinity. So I'm going to skip to that. So this whole thing will equal limit as x approaches negative infinity of x. Do your substitution, and this will be negative infinity. All right, so clearly, as x goes to infinity, y goes to infinity. That is not a horizontal line. And as x goes to negative infinity, y goes to negative infinity. That is not a horizontal line. So there are no horizontal asymptotes here. Neither one of these produced a y equals, a value, a constant. All right? Okay. All right, so that's actually going to be it. So you want to stop the video and complete the classwork.